Okay, so by using the product property, we saw that we could put together, if we had like the square root of 3 times the square root of 9, since those indices were the exact same thing, then we could go ahead and put those together and say that's the square root of 3 times 9, which would then be the square root of 27. Okay, well, if we can go forwards that way, because these are equal, that means that they are the same. So we should be able to go backwards also and get back to where we started. So if we started out with something like the square root of 27, we could legitimately break that apart and say that is the square root of 3 times 9, because that is 27. And then, sort of reversing that product property, we could break these up into two different square roots, the square root of 3 times the square root of 9. Now, by doing that, we can take the square root and simplify each individual part, because the square root of 9, that is a perfect square, that's a 3. And then we still have this square root of 3 that we can't simplify any further. So if we were given the square root of 27, we could actually simplify that into 3 square roots of 3. This is called simplifying a radical, and that's what we're going to be doing in these next few problems. Now here we have our rules for simplifying radical expressions, and this is exactly what we just went through right here. The exact same steps, breaking up your radicand into a perfect power, then separating them out, and then simplifying each one. So let's work an example and see how this happens. Here we have the square root of 50. Well, 50 is not a perfect square, but we can rewrite 50 as 25 times 2. Now we can take the square root of each one of those. That's kind of going backwards from that product property. And now by doing that, we can take the square root of 25. That's a perfect square, so it's 5. We can't do anything with the square root of 2, so we leave it as is. So that tells us that the square root of 50 actually simplifies into 5 square roots of 2. Not too bad. The biggest thing here is that you really have to be comfortable with your roots. Okay, so here we're doing one with a cube root. So we need to think about our perfect cube powers, and hopefully you've made a list of all of your perfect powers, perfect squares, perfect cubes, so that we can work with that. 54 is not a perfect cube, but we might be able to think of two things that multiply together to get 54, and one of those needs to be a perfect cube. So if you think about your list of perfect cubes, you have 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. 27 is a factor of 54. In fact, if we did 27 times 2, then we would end up with 54. So what we can do here is we can now take the cube root of each one of those. Because the cube root of 27 is 3, we can go ahead and simplify that. And then the cube root of 2 we can't do anything with, so we have to leave this as 3 times the cube root of 2. Now lastly, we have this fourth power. And again, fourth powers work the exact same way. We need to, 32 is not a perfect fourth power. But if we made a list of our perfect fourths, 1 to the fourth would be 1, 2 to the fourth would be 16, and 16 is a factor of 32. So we could rewrite this as 16 times 2 to give us 32. And then we could break those up and say, let's take the fourth root of each one. And then I'm going to go ahead and leave the m to the fourth out here, because if you've been practicing, then we know that we just really divide the power and the root in order to simplify. So now we could say the fourth root of 16 is 2. That's perfect. 4 goes into 4 evenly one time. So that root would just leave us with an m. And then here we have the fourth root of 2. Now because we were taking a even root, we have to ensure that this variable is positive. So don't forget, we have to put the absolute value bars around that in order to be truly correct.